Hey everybody, welcome to Bill Sky, the assembly guy. What we're going to look at today is we're going to look at the CPU registers for ARM processors, ARM processors. Now I already did one of these for the Intel x86-64 architecture. We're going to take a look at ARM. Quite a bit different. There are some similarities, but quite a bit different. So let's get started. So just like in Intel and AMD processors, what are the CPU registers? CPU registers are hardwired variables which are etched into the CPU chip. These are used to store data, do arithmetic, indicate the status of the CPU. They just are the heart. They're the memory of the CPU. So I like to think of the CPU as the brain of the computer, the arithmetic logic unit, which is part of the CPU, the Booth multiplier, the control unit. There's other units in there. Those are like parts of the brain. So the CPU overall is the brain. These are different parts of the brain, and the registers are the short-term memory that are put into that are used by the CPU to get things done. Long-term memory is primary storage, secondary storage. Primary storage being memory chips, secondary storage being things like hard drives, SSDs, things like that. Now there are different types of registers in the ARM processor. There's general purpose registers and there's special use registers. General purpose registers are the ones mostly used by programmers, so we're going to concentrate on those. We will talk a little bit about the special use registers, but not a whole lot. So there's two different ARMs that we're going to look at. We're going to look at the 32-bit ARM, which is like the older Raspberry Pis, and then we're going to look at the 64-bit ARM, which is like the newest Raspberry Pis, as well as the M1 and M2 chips on the Apple Macintosh computers, their newest ones, and then other type of RISC processors, which we'll talk about the difference between those later on in this series of videos. So what are the ARM 32-bit registers? The 32-bit registers are R0 through R12. Actually, the way that the architecture talks about the general purpose registers is that they're R0 through R30. However, I like to stick with just the R0 through R12 because those are not used by anything. Those are things that I can use. Now the R13 to R30, those are general purpose registers, but they're also shared with special use registers, which we're going to see an example of that in just a moment. So unlike the x86-64 architecture, the ARM general purpose registers are all usable by the programmer. They're also not split up. If you took a look at that video, they're not split up into smaller registers. Now when we get into 64-bit ARM, we will see a little bit of this splitting up, mainly for compatibility purposes. So as I said a moment ago, this is a picture of the general purpose registers for x86-64. We're looking at the EAX 32-bit register, and if you haven't seen that video, that's what we talk about in that video, is how they're divided up. Now, Intel chips are still probably the most popular chips out there for desktop computers and servers. So you really do need to know this information as well, but ARM processors really do not split things up the way that the Intel processors do. Now, what are some of the special use registers? We talked about the general purpose registers. What are some of the special use registers? There's the IP register, which is the intra-procedure stack register. It is shared with R12. That's why I don't like to mess with anything outside of that area. We have the stack pointer, which is the R13. We have the link register. We have the program counter. And all those are shared with R registers. However, there is one here, the APSR status register. It is not shared with any of the R registers. And what it is it is the register that tells you the status of the CPU. Okay, that's the ARM32. Let's take a look at the ARM64. Now the ARM64 general purpose registers are X0 through X15. Those are the 64-bit registers, and then we also have W0 to W15, and those are directly related to the X0 through X15. So W0 is related to X0, W1 would be related to X1, and so forth. That's the 32-bit component of those X registers, the W registers. And these are basically the lower half of the X registers, which are 64. Now W16 through W30 X16 through X30, those are general purpose registers, but they're also used by some of the special purpose registers as well. So here's an example of an XN. Put N, instead of N, put 0 through 14 in there. Or actually, I think 0 through 30. The X registers are 64-bit. The W registers are the bottom half of the X registers. The 32-bit registers, that's the W. Now, why did they do that? Mainly for compatibility reasons, because ARM processors started off years and years ago as 32-bit registers. They've always been that way. But with the advent of 64-bit CPUs, they had to come up with some way of making them compatible when you go from 32-bit to 64-bit, and that's how they did it, much the same way that the Intel x86-64 registers are set up. So the general purpose registers, the W16 through W30, those are the 32-bit general purpose registers, but they're also shared with special use registers. Same with X16 to X30. W16 is associated with X16 and so forth. Now, the programmer may or may not be able to use those registers. I pretty much stay away from them all the time for safety reasons, because I don't want to overwrite something that may have been put into that special use register or that W or X register. I think 15 registers are more than enough to get most of everything you need done. So I just ignore them. Now in 64-bit, what are some of the special use registers? You're going to see some commonality here. The IP0, IP1, those are inter-procedure call stack registers. And we may talk about that later on. You can look it up on the internet if you're really interested in what those are. And that's the X16, X17 registers. Then you have the stack pointer, which is actually independent of any of the general purpose registers. You have the link register, which is associated with the X30 general purpose register. You have the program counter, which, as you see here, has nothing to do with any of the general purpose registers. And then you've got the NZCV register, and that's the status register for ARM64. So that will tell you whether or not there's been a 0. We'll talk about that in a little while. Let's take a look at a debugging demonstration in 32-bit, just so you can see how to debug. Now, debugging in ARM on Linux, x86 Linux, is quite a bit different than using KDBG or DDD, as we've done in previous videos. So let's take a look at that right now. Okay, so here's our Linux. This is a VMware guest operating system running on a Mac Pro desktop computer, which is an Intel computer. I installed all of the ARM 64-bit programming libraries to allow me to write ARM code, assembler language code, on my x86 VM guest and computer. I have another video for that. I'll put a link down in the description of this video so you can do that if you haven't done that yet. So I'm going to assume right now that you've done that, and I've downloaded the templates that I've provided to you guys. You can see another Komanetsky video downloading the Komanetsky libraries for Linux. That's video. I'll put a link for that as well, just in case you haven't done that. And those are free to you. You can use them as much as you want. So let's take a look at a 32-bit. So I'm going to right-click on my Linux ARM 32-bit template, and I'm going to say extract here. And I'm going to go into, now I'm going to rename this first. So I'm going to call this ARM 32-bit red demo. And I'm going to open that up. I'm going to open it up with my editor, and there's my editor. Now, one thing in this particular template I don't like, I'm going to change it. If I've already changed it, then you won't see it, is I don't really have a data section here. So I'm going to create a data section. And I always like my variables to be put in an explicitly defined data section. So I'm going to save, and I'm going to build this just to make sure it works by clicking Build Make, and everything worked great. I'm now going to go into where the executable is. Here's my executable. I'm going to right click on that, open in terminal /main, and it printed out hello ARM32. So we know that the build process worked. Now I'm going to leave this window open over here. So let's go ahead and put some data in some registers. Now, if you take a look at this template, you can already see some things. I put a literal 1 in R0. I put the address of the message variable in R1. I put the address of the length variable into R2. I put the literal 4 into R7, and then I interrupted the operating system, asked it to do something. So we'll be talking about that more, but let's do something. So LDR means load register. So I want to load the register. I want to load the R0 register. You can lowercase or uppercase, it doesn't matter. And I'm going to load an immediate value. So I'm going to say equals 0x1, 2, 3, 4, 5, 6, 7, 8. So R0 is a 32-bit register. That's going to be 8 nibbles. So 1, 2, 3, 4, 5, 6, 7, 8. No problem. It should load it. I'm going to build it. There it is. And now let's do some more, and then we'll go ahead and do some debugging. So now let's load just a byte. So I'm going to do an LDRB, so load register byte. Again, I'm a little obsessive compulsive, so I'm going to now put R0. So this is just going to load a single byte, 2 nibbles in a byte, and I'm going to go ahead and clear R0. And then I'm going to load a half word. So a half word is smaller. It's 2 bytes instead of 4. And let's put that in R1. And I'm going to say 0xabcd. And let's clear out R1. Instead of clearing out R0, let's clear out R1. Okay, so all I'm doing is putting stuff into the registers. Now take a look at the moving data in and out of a CPU to get more information about how to do that. This is just a quick little introduction. And then let's go ahead and build this. All right, built just fine. Now debugging on ARM is a lot different. There aren't a whole lot of debugging tools for ARM assembly language, so we're going to have to use the GDB debugger. Now in my template, I actually created in the make file, I created a way for you to do this. That's semi-graphical interface. And the way that you do it is you open a window. I'll do this again. I built it. I'm going to right-click on the background, say Open in Terminal. And I'm going to say Make Debug 1. Oh, maybe it was capital. Make Debug 1. What just happened there? So I'm going to take a look at my make file. And oh, I have an old version of the templates. So I'm going to go ahead and download a newer version of the templates, and then I'll show you that make file and what I'm missing here. Okay, I fixed my problem. I went ahead and downloaded the newest templates, and let me show you what I did in the make file. So there's a couple of new targets, and I do have a make file video out there as well, so take a look at that if you're wondering what this is all about. And we have the debug 1 and we have the debug 2 targets. Now what that's going to allow me to do is I'm going to open up a single window. So I'm going to right click on my background and I'm going to say Make Debug 1. And what that does is that enables the debugger to be able to communicate, or that enables the program to be able to communicate with a debugger, now a remote debugger. Now I'm going to have to open up a new terminal and type in Make Debug 2. And now I've got my debugger, and it's kind of a semi-graphical user interface debugger. Not quite. Now I want to leave both windows open, but I'm going to go ahead and put this one up there. I'm going to put this one over here, and we can kind of see our code. I'm going to go ahead and bring up my actual code here, and we're on the very first line of code. So here's my source code. You can see that highlighted is that source code there. And what I'm going to do is I'm going to type the S character and then press enter. So that executes the first line, which was the move 1 to R0, and it goes on to the next. You can see it on the top of that window now. We can see our registers. So I'm just going to go step by step. Okay, so now it went ahead, for some reason, and I don't know why, it went ahead and it executed the LDR 0. It actually executed this one right here. And you can see that up here on the register. So we moved 1, 2, 3, 4, 5, 6, 7, 8 to the R0 register. I'm now going to now I'm on this line of code right here, and I'm now going to step. Oh, 2 S's invalid. I'm going to do 1 S, and we can see that it is now AB. It moved a single byte into the R0 register. Now I'm on this one, it's going to clear out the R1 register, so we're not going to be looking at R0, we're going to be looking at R1, which is right below R0. So I'm going to type S, enter. And now R1 has a 0 in it, R0 was left alone. I'm going to step again, and now R1 has A, B, C, D, and that's what we did right here. So if you want to learn more about how to move data into the CPU and move it into memory from the CPU, take a look at that video. And I think what we're going to do now is we're going to try this in 64-bit. But before we show this in 64-bit, I want to show you how to get out of this debugger. So when you're done, you can either press type C to continue. That will end the program. Notice how this original terminal on my debug 1 is now blank because the debugger told the program you're done running. So in my second window, I'm going to type Q to exit the debugger, and now we're done. Okay, we're back. Let's go ahead and do the 64-bit demo of this. I'm going to right-click on my 64-bit template. I believe I updated that. And let's go ahead and rename that. Let's open it up. Let's take a look at our code. Okay, now in the 64-bit version, I did put a data section, so I didn't indent everything the way I should, but I did put it in there. And you may have a newer version of the template, so you may not have any of that. Okay, so let's go ahead and do this on 64-bit. Now remember, the registers on 64-bit are X0, X1, X2, X3, and then the 32-bit version, the 32-bit copies of those, the lower half of those X registers are W0, W1, W2, W3. So I showed that when I originally described those. So let's go ahead and let's do a load register. I'm going to load into X0. That's the 64-bit X0 register. I'm going to load a large number, hexadecimal. Very large number, in fact. Let's save and build that. All right, built great. You can see no problems down here. Okay, so now let's go ahead and let's see what happens when I move something in the bottom half of X0. And to do that, we say W0. And in this one, we're just going to say all nines. So we're going to move that into the bottom half of X0 by using W0. Okay, so let's go ahead and debug this. We're just going to move some, we just moved a 32-bit value into there. We moved a 64-bit value into there. 64-bit first, sorry, in the X0. Now let's go ahead and debug this. So let's make sure it's built okay. All right, looks good. And let's go in and debug it. Now, just like in the 32-bit one, I'm going to open a terminal in the project. I'm going to type make debug1. I'm going to open up another terminal and say make debug2. And there's my semi-graphical user interface debugger. Let's go ahead and bring our code up here. Yes, I know GDB is not anywhere near as nice as KDBG or DDD or Visual Studio for that matter. So we're going to take a look at these two lines of code. So let's get ourselves to line 20 in the debugger. And the way that we do that is we just step through. So we're on line 14. I'm going to step through. We're on line 15. We're on line 16, 17, 18. And now for some reason the debugger skips over line 20, but it does it. You can see up here on the top, X0 is 1, 2, 3, 4, 5, 6, 7, 8, A, B, C, D, E, F, 0. So that's cool. So now let's go ahead and step again. And this time it should we're going to be on line 21. We should be right there. Let's step. And now it's all equal to 9. Now notice though, this is one thing I did want to show you on this debug. Notice how when we put a number into the W0, which is the bottom half of the X0, all of the bits in front of W0 have been overwritten. They've been overwritten with zeros. So instead of it being 1, 2, 3, 4, 5, 6, 7, 8, and then all nines, because all nines was put into W0, it just completely replaced it. And that's a compatibility issue, I believe. So that's our demo of 64-bit ARM registers. Okay, we're back to the presentation. Let's take a look at the status registers in the ARM processor. So status registers in ARM are there to have a status or a status of the CPU at any time to see whether there's problems, whether there's been some issues with operations. And for 64-bit, it's the NZCV status register, and for 32-bit, it's the APSR 32-bit. Let's take a look at what each one of those does. The ARM32 APSR register, bit 31. Now remember, the status register is a whole bunch of bits. So bit 31 is the end flag. If an operation resulted in a negative value, the end flag, bit 31, will be turned on. If an operation resulted in a 0 value, bit 30 would be turned on, otherwise turned off. That's the Z flag. If there was an unsigned carry, in other words, if we tried to add something to a register and we actually went outside of those bits, we lost some data, bit 29 would be turned on if it was an unsigned operation. If it's a signed operation, the V flag, bit 28 would be turned on. And that's the same thing, is if we go outside of the number of bits that we can hold in our operation, the V flag is turned on. Those are the most common ones. There are many additional ones, but not often used by the programmer. And I put in an overview of what each one of those are. If you add two unsigned numbers and there aren't enough bits to contain it, the bit 29 unsigned carry flag will be turned on. Same for carry. The bit 28 signed carry flag will be turned on. The 0 flag will be turned on if an instruction results in a 0 value. This flag is set. If it's not a 0 value, that flag is unset. If an instruction results in a negative value, that bit 31 negative flag will be turned on. If it doesn't result in a negative value, that flag is turned off. Now for the NZCV register, which is the ARM64, is pretty much the same thing. The bits are exactly the same. You've got the N flag for negative, Z flag for 0, C flag for unsigned carry, and V flag for signed carry. Now this will all mean more when we get into conditional processing on the ARM processor, where we're asking questions, if statements, did something happen in this calculation? But for right now, that's what each one of those means. All right, so that's the end of this video. I hope it helped you get a little bit better understanding of the ARM processor and the registers and how to use them. Hope to see you at the next video.